Hello everyone, my name is Xiaxue Xu and welcome to my presentation. Today I'm going to talk you through my assignment focusing on the image recognition and adversarial attacks. This video will cover two interconnected assignments. First, I will look at assignment 4, where I prepared my data and trained three different neural networks on the MIMS dataset to classify the handwritten digit. Then I will transit into assignment 7, where I applied various adversarial attacks to test my model robustness. Let's dive into the code. The first part is I begin with load the MIMS dataset. To ensure my model could generalize where to on same data, I define an image transformation pipeline. And I also play around with data augmentation. So for the training dataset, I use the random rotations with a degree of 15 to expand the training dataset by introducing the slight visual variations, which can help us to prevent overfitting and make model more robust. After that, I convert the image to the tensor and normalize them. For the test dataset, I didn't do the data augmentation to keep the evaluation data pure. So here, after set up the transformation pipeline, I just load the data. The next thing is I build three neural networks that learn from the class to compare the performance. The first one I defined here is shallow MLP. That is a simple multi-layer perceptron contains two fully connected linear layers, which a hidden size 128. The next model I defined here is the CNN, consists of two convolutions, no layers, max pooling, and two dropout layers, followed by two linear layers. The third models I implement here is a transformer models. This involving creating a patch embeddings class with a patch size 7, followed by adding a classification token and positional embedding before passing the data through the full transformer encoder blocks. With my model defined, I trained each of them for 10 episodes. And using the item optimizer with a learning rate 0.001. And these are all the model performance. The first is MLP, and the final accuracy is around 98.24%. And the next is the CNN, which is 99.32% accuracy. The last performance for the transformer is here. Okay, here it doesn't have the output, but while all the model performs reasonable well, the CNN was the clear winner with 99.32% accuracy. The next section is the assignment 7, where I did a adversarial attack to my models. And a adversarial attack involved adding tiny, often invisible amount of noise to an image to intentionally fool a machine learning model. And I implement three specific attack functions below. The first is the FGSM, where I used to attack my models later, and FGSM calculates the gradient of the loss with respect to the input data, extract the sign of the gradients, and add it to the image scaled by the factor called the epsilon. The next is the PGD, what I apply to the shallow MLP. The PGD is a more complex iterative version of FGSM. It takes multiple small steps here, And the steps I'm choosing here is 10, and clip the perturbed image back into an epsilon bond at each steps here. MIFGSM is the last function that I use to attack my transformer model. This technique introduces momentum terms into the iterative process to accumulate the velocity in the gradient direction, which help avoid local maximum during the attack. So after define all these attack functions to evaluate the attacks, vary the epsilon from the 0 to the 0.3 and measure the clean accuracy, the attack success rate, and also the adversary accuracy to compare all the different functions. And also make a plot here to for the feature compare. The feature plots clearly show that the devastating impact of this attack. For my CNN under the FGSM attack, as the epsilon increased to the 0.3, the model is accuracy plummeted from over 99% down to just 28% here, while the ASR sorted to the 71.66%. The results were even more severe for the MLP and transformer under the iterative attacks. At an epsilon of point 0.2 to the 0.3, both models' accuracy dropped entirely to the 0%, resulting in a 100% attack success rate. That's all what I did for 2 assignments. Thank you for your time and for watching this presentation. Bye-bye.